Hi, I'm George and I'm here with another Double E video. Now, this problem here is a little bit longer. I'll add some links to the video again. I'll put them somewhere on this side of the video that will let you skip to the respective answers. So you want to see B, skip to the answer for A. You can watch the rest of the video if you want to. So let's go ahead and take a look at this. We've got some kind of Boolean, we've got some kind of transistor level schematic, and it's asking us to find the Boolean function of this schematic to find, or to change the size of only two transistors to match the pull up and pull down resistances of the entire circuit, which will help us to, match our delay. And finally, to find the propagation delay of this original circuit without the modified transistors. If we hold 3 over 4 inputs at 0 and transition the fourth, the input C, from high to low. So let's go ahead and get started with A. So we're wanting to find the Boolean function implemented. Let's just go ahead and zoom into this. We're going to take care of this one stage at a time. That's the easiest way to handle this. So we have from VDD down. Actually, we'll look at this from on the NMOS side. Remember that with a CMOS circuit, since the two halves are equivalent, you only have to look at one half of the circuit. So we have this, which is A plus B inverted. The same thing is true down here. You have C plus D inverted. Now, let's go ahead and look at the output. So, you have, and I'm just going to call A plus D, or A plus B, I'm just going to call this E, and C plus D, I'm going to call F. So, you have E and F. And what is this circuit? This is E and F inverted. So, what does this mean? This means that our complete Boolean function, if we go ahead and plug in this for E and this for F, is equal to the inverse of inverted A plus B and inverted C plus D. Let's go ahead and start doing our inverses. Now, keep in mind, you could do this with PMOS, but I wanted to do this to kind of show you what happens when you have to go back and invert these signals. So, you know that inverted A or B is equal to non-inverted AB, and this is AND, same thing with CD, and this is still all inverted. We can rewrite this as A and B and C and D inverted, and you know that when you go ahead and inverse these ANDs, you end up with A and B and C and D. Therefore, this circuit is a 4-input OR gate. There you go. So, that's the answer to A. We have a 4-input OR gate. Let's go ahead and see what's going on with our equivalent resistances. So, starting part B, I'll go ahead and copy the schematic, paste it down below. So, to figure out what we want to figure out which transistors we want to change, we're going to have to look and see what our resistance values are in the first place. So, let's go ahead and zoom in, and I'll look at this again one stage at a time. Now remember that for PMOS, our resistance values, our equivalent resistances, are 2R over K, where K is, let's zoom in, this number right here, the width. Because we know that these are width over length ratios, therefore, these PMOS that are 4 over 1 are 2R over 4, or equal to R over 2. So, and remember also that with NMOS, it is simply R over K. So if we look at these these two transistors down here, R over K is just equal to R. So let's go ahead and look at what the deal is with this top half of the circuit. Let's zoom back in. Now, as I said, let's use a different color that will show up. This equivalent resistor has a value of R. So does this. Now, because we're only looking at worst case scenarios, we're just going to look at one of these since they're in parallel. So, our pull-down resistance is equal to R. Our pull-up resistance, as I just said, we have 2R over K, which leaves us with R over 2. So, this is R over 2. This is R over 2. Goes up to VDD. Now, because they're in series, we add them together. So you can see that the top half and the bottom half, they're parallel. Let's look at the other input circuit. You can see that this is 4 over 1, 4 over 1, 1 over 1, 1 over 1, same story. This is R over 2 plus R over 2. We can disregard either one of these, it doesn't matter which. And this is R. So this equals R. Our pull up and our pull down, identical. Finally, let's go ahead and look at our output stage. Now, this is our pull up network. These have a width of 4 over 1. However, you can see that they are in parallel between the output and VDD. So, we can disregard one, doesn't matter which one, and we have 2R over 2 equals R over 2. Looking down toward the output, or looking down toward ground on our NMOS side, we have, now remember with NMOS, it is simply R over K. So, this resistor is R over 2, this resistor is R over 2. That leaves us, if we add these together, with a pull-down resistance of R. So, you can see that on the output stage, our pull-up and our pull-down networks are not matched. So, how do we choose which transistors to resize? Well, that's simple. Go ahead and look back here at the question, and it says we need to change the size of two transistors to match the worst case pull-up and pull-down resistances. Well, our worst case is R. On our, on both input sides, the worst case is R. Therefore, our pull-down network, which is R, fine. We need to change our pull-up network to make it R over 2. Let's go ahead and redraw just the pull-up half of this so that we can see what's going on. So, 1 PMOS, 2 PMOS. And this is E, this is F. VDD, VDD. Now, what we want is now remember that these are parallel, so we only need to worry about one of them. Now, we want, and this is an easy way to figure out what you want your value to be, we're just going to say that we want a value of R. We know that a PMOS has a value of 2R over K. Therefore, all you have to do is solve for K. So we can go ahead and bring our R down here, K to the other side. We end up with 2R over R equals K. Therefore, K equals 2. What that means is that you resize these PMOS transistors, both of them, because you want both worst case scenarios to be the same, to be 2 over 1 width to length instead of 4 over 1. That's your answer to B. Simple enough. So, let's go ahead and take a look at the last problem. This is the one that might take a little while. In fact, it'll take so long, let me get a drink. Alright. So, we're going to consider a case where A, B, and D equals 0, and C switches from high to low. So we want to estimate a propagation delay. Let's go ahead and paste a new copy of the circuit. Alright, zooming in. Again, we're going to handle this one stage at a time. Now we're looking for propagation delay, which means we're only interested in the parts of the circuits that are going to change. If you look here at the AB side, this is 0, 0, 0, 0. This doesn't change. It is important, however, to know what our output is going to be. So if these NMOS transistors down here both have an input of 0, they're both open, which means that which means that there's no current traveling through. However, the PMOS transistors are closed, which means that you have current traveling through them, which means that this line right here has a value of 1. Let's go ahead and look at our other side here. So this is 0, this is 0, this is 1 to 0, this is 1 to 0. Now you can already know intuitively that this transistor is going to close, creating a value of 1 on the output of this stage. And you know that this one was closed, but it's going to open, and this transistor is already open. So this is all we need to look at. We know that our circuit path is going to be in this direction. Our path of how do we put this? The path of propagation is going to be from VDD down through the PMOS part of the circuit into the second stage, our output stage. Let's take a look at what happens over there. Now, we know that these guys have a value of 1, which means that this guy turns off. And let's see here, and this guy turns on. We know that this line also has a value of 1. If we follow this around, that means this guy turns on, this guy turns off, which means that our path of propagation will be in this direction. Now, it doesn't travel from the gate to your drain. That's kind of misleading the way I drew that. Your path of propagation will actually be from ground up, which means that your current will be traveling from your output to ground. Now, it's important to keep that in mind, and let's see here. And that's really it. Now we're going to get to the point where we're going to start drawing our equivalent resistances and capacitances. And here's a trick that will help you determine what you want to, how you're going to assign things. Let's go ahead and blow this guy up so we make it easier for us to write. Alright, starting again at the input stage. Now, you know that then our path of propagation will be this way. Therefore, our resistances will be through those transistors. It makes sense, our current's traveling through there. Those are the equivalent resistances that you're going to consider when you're calculating your Elmore delay. These guys, resistances don't matter, but they don't go away. You have to consider their capacitances too. Now, one trick that I found, and it works in an IC Design 1 class, as you travel on through and you deal with more complicated circuit topologies, this trick won't necessarily work. But in this case, in this class, with these circuits, you can take your equivalent capacitances and just draw them on the side of the transistor closest to the output. Okay, I'm going to say that again. On the side of the transistor closest to the output. So, this transistor right here, this is closest to the output. Therefore, your equivalent capacitor is right there. Same thing with this guy, with transistor C. This part of the this side of the transistor is closest to the output. Therefore, there is your equivalent capacitance. The same thing goes with your NMOS side. I'll go ahead and erase these because we're going to redraw it here in a second anyway. These sides of these transistors are closest to your output. They're on your output. Therefore, they get the capacitors. So, if we go ahead and redraw this as an equivalent RC model, we're going to go ahead and write our VDD, our resistance of C, resistance of D, and our output. Now, we have our capacitance of C right here. We have our capacitance of D right here. We also need to consider the other capacitances on the output. So, capacitance of NMOS C, capacitance of NMOS D, And notice that I'm drawing all of these to ground, technically because we're dealing with switching everything. All of the DC components, or all of the DC rails, are effectively ground. So you can draw them all as ground. And then that'll come in important when we start combining these together. Now, we're not done. These are all of the equivalent resistances and capacitors for this stage, but we also need to consider our output capacitance. How do we find that? Well, let's take a look at what what this circuit is connected to up here. So, it's connected to this transistor. It's connected to that transistor. 4, 6. Therefore, you have to deal with this transistor's equivalent capacitance as well as this transistor's equivalent capacitance on the gate. Now, keep in mind that at least with this kind of topology, or with these kinds of transistors, with this technology, that our capacitance for NMOS and PMOS are the same. And it's just equal to, your capacitance is equal to C times K, where K is your width of your width over length ratio. So, coming down here, we know that this capacitance is 4C. This capacitance is also 4C. This guy is 2C. This guy is... No, they are just C. I apologize. C and C. We also have to talk about our input capacitance of our next stage. And I'll just draw these like this because we have one going through NMOS, one going through PMOS. They are 4 and 2. 4C, 2C. And also we have our equivalent resistances. Now, we determined those up here. If you remember how we did this, you know that this equivalent resistance is R over 2, and so is this. So, this is our equivalent circuit for this stage. The easiest way to analyze this is to combine our equivalent capacitances together so that we have a simpler looking circuit. So, let's go ahead and do that now. We're going to take this guy, and I'm just going to move it so that it's easier to work with down here. Alright, so we're going to start right here at the beginning of our path of propagation. Going to draw the ground. We have a resistance, R over 2. We have a parallel capacitance of 4C. We have another resistance of R over 2. And then we have a parallel capacitance. Now, you can see that these, and this are all in parallel. Therefore, we'll just add them together. 4, 6, 8, 12, 12C. And that's our equivalent circuit. All you have to do now is perform the Elmore delay analysis. And all you have to do now is perform the Elmore delay analysis. Now, this isn't the end. This is the first stage. We also have to consider our second stage. Now, our second stage is not directly connected to this. Our second stage will be over here to the side, where we have some kind of voltage, where current is either passing through or being shunted to ground, and the rest of our circuit. Let's go ahead and see what that circuit is. Now, we'll move through this one a little bit more quickly because we're more familiar with how this works now, I would expect. So, we have these two PMOS transistors. They're both going to VDD. So our equivalent capacitances are right here because these are the closest to the output. We have an equivalent capacitance right here, closest to the output. Same here. Now, our path of propagation is through here. Therefore, our resistors go right there. Redrawing this, we have ground, resistance, capacitance, resistance, capacitance, another capacitance in parallel with that guy, and our output. Now the problem doesn't define any kind of input capacitance for the next stage, so we're just not going to draw that in here. So what are these capacitor and resistor values? Well, we can see that our NMOS resistors have a value of 2 over 1. Therefore, our resistor values are simply R over 2 and R over 2. Capacitors, because the NMOS have a value of 2, 2C, 2C, the PMOS have a value of 4 as far as their width goes, so it's 4C, 4C. So if we go ahead and take this, and we'll move it down so that we can redraw it. Right there. Here, I'll move this up here to make it easier to work with. So, since the path of propagation, we're going to define it as starting from here, and you can see that this is effectively like a negative voltage because all the current's being shoved through it. We'll say that, that's our voltage. There's our first resistor, R over 2. There's our parallel capacitance, 2C. Another R over 2. And then 4, 8, 10, 10C. So, all you have to do now is compute your Elmore delay. So, what is Elmore delay? Well, I'm glad you asked, because we'll do that right now. So, looking at the first stage, we have, and so there's 2 ways of doing this. I'm going to show you one way. There's lots of tutorials showing you, different ways of doing this, and I'll show you the way that I find success with. So I have R over 2 times all the downstream capacitors, and that is 4C plus 12C. Now, this is plus the next resistor, R over 2, times all the downstream capacitors, which is just this 12C. So you have R over 2 times 12C. And this ends up becoming R over 2. And let's see, we'll go ahead and do some factoring here. This is 16C, that's 12C, so 16 plus 12, which is equal to R over 2 times 18, 28, 28, which is equal to, let's see here, 28 divided by 2 is 14 RC. So, that is the Elmore delay of our first stage. Now we need to find the second stage. And we're going to calculate it the same way. R over 2 times downstream capacitors, and I'll just write them as 12C, plus this guy times the downstream capacitors, 10C. So we do some factoring, we get R over 2 times 10 plus 12C, that is equal to RC over 2 times 22, which is equal to 11 RC. Now, we have the delay of the first stage, we have the delay of the second stage, all we have to do is add them together. Therefore, our total delay is 14 RC plus 11 RC, which yields 25 RC. And that's it. So, that's how you calculate the Elmore delay of a Boolean function, represented by, some kind of transistor level schematic. I hope you enjoyed this video. I hope it was enlightening and educational for you. I hope it helped you as much as these videos helped me. And as always, good luck.